In 2007, Protection Engineering Consultants began a research project for the Transportation Research Board Airport Cooperative Research Program. The goal was to develop improved civil aircraft arresting systems. Any number of things could cause a plane to overrun the end of a runway and roll right off the end of it. Arrestor systems that would stop such a plane are called EMAS, or Engineered Material Arresting Systems. There's really only one approved civil aircraft arresting system, or EMAS, so if you need a arresting system, you only have one place you can go to get it. And the lack of competition, the lack of choices, the cost of the current system, the maintenance needs inspired the FAA and the National Academy of Science to look at how they could sponsor a research effort to try to spawn more alternatives. In 2009, we ended our research. ACRP Report 29 for Developing Improved Civil Aircraft Arresting Systems summarized the findings of that program. And in it, we recommended two possible systems as viable candidates for FAA-approved EMAS systems. About a year later, we began this research effort for a Norwegian company that manufactures a material made for one of those two candidates, and that is called Norsk Glassgjenvinning, or NGG. NGG manufactures the material Glasopor, which was one of the two candidates that we had looked at and recommended for possible development. The advantages of a Glasopor EMAS system would be several. First, the primary constitutive material is recycled glass. The goal for the Glasopor system is to have what we call a pour-in-place construction. Instead of building blocks in a factory and then bringing them out to the test site and putting them in place one by one, Glasopor can actually be brought out loose, poured in place, leveled to the right height, and covered with a permanent cover layer. The loose fill properties of the material allow us to entertain various installation methods that you really don't have when you're dealing with fragile, cementitious foam blocks, which gives us a completely different construction approach, one that offers the promise of significant cost savings from a standpoint of installation and overall manufacturing costs. When we go to an actual airport and want to install a Glasopor EMAS-bädd, we would look at the design fleet of aircraft for that particular facility. We would tailor a specific arrestor bed design, which would be a grade of Glasopor, a certain thickness of bed, and a certain length of the bed, with a certain setback from the end of the runway, that would function well for all the planes, ensure good stoppage at our design overrun speeds between 40 and 70 knots, and provide for the smallest arrestor bed that would accomplish the job in that available space, thereby minimizing cost and ensuring good performance. The current research effort is intended to commercialize the NGG Glasopor EMAS system and do whatever is necessary to meet the requirements of the FAA Advisory Circular for EMAS.
To further investigate the characteristics of the Glasopor, we did both small-scale and large-scale testing. Large-scale testing consisted of an idealized strut from an aircraft running through a test bed. This test bed is 9 feet wide by 400 feet long. It's got ramps at each end that come down 50 feet from the end, so it slowly lowers the tire into the material.
The testing program that we're doing out here at Texas Transportation Institute is largely designed to meet the requirements for full-scale testing. So there are two tracks in the FAA Advisory Circular that you can follow for full-scale testing. One is to use a plane, and the other is to use what they call a one-wheel equivalent. And in order to do that, we fabricated a novel test apparatus that we call the test bogie. It was fabricated by Progressive Engineering Services in Bulverde, Texas.
We have three major systems installed on the bogie. We have compressed air, we have hydraulics, and we have electrical system. The compressed air is used for braking and for adjusting our suspension, so that we can attune the ride height of the bogie. The hydraulic system is used to apply a vertical force down on the aircraft tire. Powering the hydraulics, we have a pump on a reservoir, and that pump is powered by our electrical system. The electrical system, in addition to powering that pump, is used for all of our data acquisition. We have sensors all over the bogie used to give us information on what is happening while this aircraft tire is going through the bed.
The entire purpose of the test bogie is to simulate an actual aircraft strut running through an arrestor bed under full weight, the same kind of weight that a real airplane would produce at full speed. And it's been very well instrumented to measure both the loads, penetration into the bed, speed of run, a host of other factors. We've got a a whole smattering of instrumentation on it.
The data we collect from the test bogey is funneled into a laptop during the test. We do all sorts of transformations to the data to work it into something usable, to something intelligible, to validate our results.
It's impossible to conduct physical tests on every plane that's out there. What's necessary is to conduct enough tests so that you can prove that you have a very accurate predictive computer model. And then using that computer model, you can simulate any plane that you need. When the NGG, Glasopor, EMAS systems are designed and installed at airports, this high-fidelity predictive model will be driving the design from the background. And that is how we will determine what the landing gear loads would be on any plane and make sure that we're both safe and we're not going to overload the landing gear, at the same time that we decelerate the plane quickly and bring it to a controlled stop. So at the conclusion of the test effort, we now have a very strong understanding of the dynamic performance of Glasopor when used as an EMAS system. And we have a strong basis for calibrating our high-fidelity computer models. Those computer models will then be used for predicting overrun performance for any plane that we choose to look at in the future. So the Glasopor EMAS system offers us the possibility of lower installation costs, reduced maintenance requirements, and a longer lifespan for the system.